Okay, so welcome to everybody. Today we have the talk of Professor Kähler from University of Aveiro about Ruzhansky-Turunen-Wirth calculus in the case of spin groups. So thank you very much, Professor Kähler, for accepting our invitation. So you can start.
So thank you very much, and thank you very much for giving me the opportunity. As you can see from the title, I'm talking about something which actually was developed by other persons, especially Michael Ruzhansky-Turunen-Wirth. So on that calculus, I would say the real expert is actually in the audience. But the point basically is that's a general scheme how to construct Fourier transforms, and with that one also pseudo-differential operator calculus over compact groups. And we look here at the special case of spin groups, which is particularly from applications one thing, but also from other aspects you will see along the side. Now, let me start with it, and let me actually put a kind of question to the audience, how familiar you are with pseudo-differential operators. I mean, I can give, if not, I can give some small things, but I mean, considering that I'm right now here talking mainly to the Ghent group, they should all quite familiar with it. In any case, if somebody doesn't really know, basically here's just simply, we all know that over the Rn, if you have a linear translation invariant operator, of course, it's just on the Fourier side a multiplier. And with that one, we have the standard formula for that. And of course, you can basically have your symbol and then basically pseudo-differential operator for that one. And characteristics are actually, well, any differential operator is basically just the characteristic polynomial. And we have also simple classes. That's the usual definitions. There's nothing special on that. And Laplacian, I think everybody's familiar with it. And also fractional Laplacians and so on is actually working on that. So I don't want to actually spend too much time on that, because the more interesting part for you will probably come a little bit later. So there's also kind of selection of results. In fact, as you can see from also the papers, if you have the basics, etc., there's a kind of machinery with that one. If you have the basic calculus, then there are a lot of things, results you can basically generate from that. And there are a lot of cases were actually studied in the literature, especially also by your group, but also by other persons. The simplest, so we will later on come back to that. Here in this talk, I will in the end mainly focus on hyperellipticity and ellipticity and parametricis here for that part. But of course, one can also do all the other things quite easily afterwards if the basics are established. So, well, I guess if one would ask Michael Ruzhansky here, we can ask him how to construct a Fourier transform. There are basically two approaches he actually developed and popularized. I will actually go inverse to the things you can find in the literature. One thing is basically use the eigenfunction of an operator. So here you can use M as manifold with boundary, but you can also just use, for instance, a compact manifold without boundary. Then you basically have, for instance, Laplace-Beltrami operator, and you know a priori that thing has a discrete spectrum, and with that one, the discrete set of eigenfunctions, and you can use them for that part. So, and one can always use that part. More important for us here is a second approach, which is basically using group representations. And now it gets interesting. Basically, I just look for a unitary representation of a group. So we have a group, we have a Hilbert space, we have the representations in the Hilbert space, and we want the representation, of course, unitary, and that's preserving the group structure. That's basically what the representation is. And we look for irreducible representations, such that basically you take basically entire representations and then you chop it into pieces, and irreducible means you cannot chop it much smaller than that. So there's unitary dual always defined. So if you draw the equivalence classes, we can basically say that the unitary dual are a continuous irreducible unitary representation of G. Attention, in general, that is not a group. If you have, in the case of abelian groups, then of course you will get a group, but in general, it will not be a group. And the Fourier transform is then defined in that way. The question, of course, immediately comes up what kind of groups one can use. I mean, the standard example you have is basically using the translation group with over an interval with periodic boundary conditions. So basically the torus. And then you have basically an abelian group. The next thing would be basically LCA groups, so locally compact abelian groups, because that's basically saying Rn again. So, but the question is simply what to do in more general cases. And that's also linked actually with the previous questions, because one of the ideas, if you want to do things, which we don't do here, but which one can do, is basically if you have a group, G, and a compact subgroup, K, you can consider the Gelfand pair, which is basically just the group factorized K from one side and the other. And that basically means immediately, if you keep in mind that, okay, let me switch to the other side. No, not this one, that I can write a little bit. GK, if you factorize out G from one side and from the other side, then of course, we know that we have the Cartan decomposition. So for any group, you always have that decomposition KAK. And that means where A is abelian, that means in such a case, KGK has only 1D irreducible representation spaces. And that's actually, which basically means that you can basically say, take this one and take the Gelfand pair and take the irreducible representation about that one, and you basically get a classic representation with discrete spectrum where each one actually corresponds only to one thing. That's actually in the case of spin groups later on, or SON has been done in the past, which is actually what you get for the case of SON. That's what you get actually if you use the Laplace-Beltrami operator. So if you look at Trami if operator, that you basically build with, take the eigenfunction of Laplace-Beltrami operator, that's usually what you get. So for instance, basically, if you do that one, then you get a Fourier transform based on, if you do that one, basically for the SON, you factor out basically the lower dimensional ones. So you have something which only depends on a parameter, and that's basically then where you get the Gegenbauer polynomials. So Fourier transform based on Gegenbauer polynomials basically comes, if you do that kind of thing on the sphere, then you basically get, or SON, that you get Gegenbauer polynomials. The problem is, it's basically for each space you have one, and that means is a kind of, well, it basically corresponds a little bit that if you would take the matrix valued one, which we'll later on talk, but then you actually try to average it and use the characters. So That's basically the other way one can actually do this kind of thing. And that's actually a link where you can always, from a group, even if the group is non-compact and so on, you can always end up with a representation or an operator which corresponds to the first one. And that's also, at least for the sphere, what was mainly done in the past. So Gelfand pairs and going back to one-dimensional subspaces, that's usually what persons like to do. We actually like to do a little bit more than that. We like to follow actually the idea of Ruzhansky and Wirth and Turunen to actually get a full matrix valued one. So with all the representations. And that's basically what the idea behind is. And that's basically also these the Fourier transform. In that case, the point is basically, well, it goes back to a version of the Peter-Weil theorem, which you can find, I think, in that form for the first time in the book of Ruzhansky and Turunen, that you can basically decompose L2 into the direct sum of linear bi-invariant subspaces. So really, the spaces for the irreducible representations, they decompose L2 and into irreducible things. And each subspace basically corresponds to one irreducible eigenspace. And if you sum them all up, you get, and then that basically means that you can get the Fourier transform just by integrating against the representations. And the inverse is basically given in this part. Point is, it's discrete, so you can put it as a sum over the dual. And well, TR here is just a trace, and epsilon, well, psi of x, f hat of x, that's basically your representation there. In a kind of way, basically, you can simply think of f hat as kind of Fourier coefficients. So, and in particular, you have a Parseval identity, which is, of course, what you definitively want. So, and from that part, you get, of course, now that comes the machinery. You have your group convolution. And of course, what you want from the Fourier transform is that it maps the group convolution into pointwise multiplication. So, and if you have a symbol, an operator with a certain symbol, then of course you want to have the convolution kernels, which you can get from that. And the main point in this calculus is you want symbol class, you want to work with it, and that means basically you need operators on the frequency side. And operators on the frequency side, since it's discrete, have to be the difference operators. So what they introduce basically is kind of difference operators coming from multipliers. So you choose a multiplier, which presents the identity into 0. And that gives you always a difference operator. So I put here the example in Rn. Of course, that's continuous, so there's classic derivative. But on the torus, that's basically the classic example. You take here the forward differences. I mean, you could also do the backward differences, but that's basically what you have. And the multiplier is just the standard symbol of a forward difference. And the question is simply, what kind of difference operators can I take so that I can generate everything, or that the calculus works? And for that one, they introduced the so-called strongly admissible set or strongly admissible session, which is basically having these conditions. And for the torus, for instance, these multipliers we have here is strongly admissible. So we'll later on look in our specific case what we will have there. For that part, the main point is basically that you can generate everything. So you actually, if you take the rank of all these together, that gives the dimension of the group you have here. So, and these ones basically, the difference operators basically play the role of the classic differential operators on the frequency side, if you think in terms of all of the phase space. And from that part, basically, then one can simply get the Hermander symbols. So that's basically the point, especially I recall C here, which is basically that you actually take now your difference operators, which you have, and with the difference and derivatives, you can get this part. I'm pretty sure a lot of the audience is familiar with it, but still, for the guys who are not, just that's basically the thing. And the point is basically that this one basically allows you to introduce Herm underclasses and the usual jazz. Also, how you actually work with operators then, that they actually map the right spaces into the right spaces and so on. So now you also have a composition formula, which of course is asymptotic. So here you have the derivatives on one over and the difference operators acting on the other symbol. And yes, and asymptotic in the sense that if you take the difference of the true symbol of the composition and this one cut off, then it's basically of a high enough well, regularity. So ideally, basically, if n goes to infinity, then of course it's basically as infinitely smooth operator. So now the question now, let's come now directly to what actually we want to discuss, spin groups. Or we want to consider this machinery in the case of the spin groups. Why spin groups? Well, the simplest thing you can see about spin groups is, of course, they are linked to rotations in higher dimensions. If I want to rotate x into another point, then in Rn, then basically you take the S from the spin group as a spinner and simply that part. Of course, you will rather be surprised for the first time see that one, why we just take SON. I mean, guys from physics, they don't have a problem with that one. They basically immediately jump to the spin groups because for them spin also has a little bit of more of a meaning than just rotations. Why not just SON? Well, the problem with SON is usually it's not a simply connected group. And that's usually, in a lot of cases, a trouble one. You want to avoid that. And spin N, you can always see as a double cover. And it's simply connected. The applications, basically, I wrote a lot of things here. If you go for, the simplest example you have is basically if you go for the electron, then you have the Dirac equation, where you have the Dirac equation du plus mu equals to 0. So m is the mass. And if you want that one for an electron, u is usually spinor valued. The problem is spinor valued is not so nice to work with unless you're really actually really diehard physicist on that part. So persons prefer to actually simply use that one as part of a Clifford algebra, R0n. I will come to that one in a minute. Another example, which is quite used, is in diffraction tomography. Diffraction tomography is basically when you actually have, let's say, I have a specimen. And then I want to measure what is inside. So you take basically a sphere around, then you send X-rays in. And these X-rays are basically going in and they are diffracted. And you would like from the measurements of the diffraction, so you have to measure all the diffractions around. And from that one, you want to know what is inside. And if you look at that part, I mean, classic radon transforms is basically you integrate over straight lines. Here, you integrate over actually great circles, which is actually you integrate over curves in spin n. That's basically another part where that one is coming from. Robotics basically means you want to move robot arms and other things around. And then, of course, you have a problem that you would like to actually work with that one. You have translations and dilations. Well, translations and rotations, dilations, you don't usually use here. So rigid moments. And the problem is translations and rotations have the problem. They are not really nicely linked. But what you can do is actually, you can embed the whole thing 2 dimensions higher, and then everything becomes a rotation. So if you take translations and rotations in Rn, you embed the whole thing in the Rn plus 1, 1. So Lorentz space 2 dimensions higher, and suddenly you can write everything down just as a rotation, which is basically one thing they like to use there, to have it not only uniformized, but also easier. So how does it work for us? Well, for that one, let me say that's not so well known, but let me say we are using one way of using spinors is not directly using spinors, but actually so-called Clifford algebras. Basically, the whole idea is you just have your vector x e1 as a span. Sorry. You have your vector, something like that. E1 x1 plus en xn. And then you actually introduce multiplication, and the multiplication has to only fulfill 2 things. First of all, it has to be anti-commuting. That's basically what is this one actually stated here. And the square can be either +1 or -1. Complex numbers are basically just, you just have one vector, E1, and the square is -1. That's basically classic complex numbers. That's also why it's commutative. If you go 1 dimension higher, so to the Clifford algebra, CL01 would be complex numbers, CL02 would be the quaternions. That's basically, then you have 3 elements, and they're all anti-commuting, and they all square up to -1. If you want to have Minkowski space, then the first one squares up to +1, and the other 3 square up to -1, so time and space. The dimension, if you have the universal one, is always 2 to the power n, and the conjugation is basically just like what you would expect. The conjugation of each basic element is minus, and it's basically switching. Same thing you would do actually for matrices. So, and Clifford algebras, you can also consider theoretic. Well, you can consider them as 2 power n times 2 power n matrices, but you don't want to do that. That's just trouble. A special thing which is always associated with Clifford algebras is the so-called Dirac operator, which is basically the generalization of the Cauchy-Riemann operator in complex analysis. And functions belonging to the kernel of that operator, so where you basically have d p q f equal to 0, they are called usually monogenic functions, and they are the generalization of the holomorphic function, and especially you usually have pq squared equals basically Laplacian in p minus Laplacian in q. And that means basically if p is 0, you basically have something which factorizes the Laplace, classic Laplace operator. So, which basically in particular means monogenic functions, just like holomorphic functions are also harmonic functions. And if p is 1, you have the wave operator, and p is larger than 1, you basically have what is usually called an ultra hyperbolic operator. That's basically behind that one. In terms of calculations, makes life easier than having to do other things. And for that one, we are going now for the representations. And let me actually switch that one. That's wrong time. And the point is basically, we need the representations. We need the representations of spin M. And there you have basically 2 types of representations. One thing is called the spin 1/2 representation, the other one the spin 1 representation. It's basically also for, well, mainly from physics where it comes. For us, let's say we have the H and the L representations, which is basically, here you have the action of the spinor itself, and then you either multiply from the front, or you multiply from the front and the back with the same thing there. So the first thing one can relatively easily see is that both are actually invariant under the Laplacian and covariant under the Dirac operator. And to construct them, there is a machinery to do that one. I'm not wanting to go too much into details, but basically you can associate to these representations, you can associate so-called weights and roots. And For us, the only important thing is you can always construct the representation via the highest weight vector. So you go for each space of irreducible representations. You take out from that, you always have the highest weight vector, and there's only one always. And then all the others you can basically just construct in the same space by just rotating them around. So the only thing you really need is the highest weight vector. And there is the following: for the H representations, you have basically two possibilities. One thing is given here. That's this case 1 and case 2. If your weight is just an entire number here of that type, then H representation are spin 1 representations here. That's spin 1 representations. So you have a weight which is only composed of natural numbers, and the last one is positive. And then you can write your representations down in these terms. These are just products. X wedge x2 is just standard wedge product, or if you want in terms of Clifford algebras, it's just, if they are vectors, you just have here the commutator. It's nothing else what that one is. And for T, you have basically Ti Tj plus Tj Ti dagger. Well, basically, let me write it actually shorter. Basically, what you have is the following: T, and later on also come T dagger, Tj, Tj dagger. All are anti-commuting. They all square up to 0. Dagger squared. They all square up to 0. And the last one you have is basically that Ti dagger plus Ti dagger Ti is 1. Just the identity. Such a basis is also called a Witt basis. If somebody wants the name, basically, that's also called in the literature Witt basis. And the idea is basically you just build them up from these puns. Such kind of polynomials where you have x1 wedge x2, t1 wedge x t2. So you basically take that one and take the inner product with the basis, etc. They're also called simplicial. In that case, simplicial harmonics. So, but they are called simplicial polynomials. In the second case, you have with the -1, it's the same thing, only that the last one here, because of the -1, is Tm dagger. That's basically the thing you have here. That's for the spin 1/2 representations. And for the L spin 1 representation, for the L representations here on the spin 1/2 representations, you basically take the half integers here. There you take the half integers, and basic polynomials look similar to that part. T1 dagger, etc., all the things. And below also. And there's an interesting case, which is always the difference. I mean, there's geometrically, if you look into Rn, there's always the difference between even and odd dimensions. They always behave, even and odd dimension behave differently. If you look at the Radon transform, if you look at everything, you will always realize even dimension have one behavior, odd dimension have another behavior. And in this case, the odd dimension case is actually insofar easier that you only have one pair. So in the odd dimensional case, you have basically just the case 1 here, only these representations. So in the odd dimensional case, you only have this. And the same thing of spin 1/2 representations. In the odd dimensional case, you only have this. While in the even dimensional case, you have both of them. In the even dimensional case, you have both 1/2 representations and both 1/2 representations. So all cases appear there. That basically is why the even dimensional case is always different to the odd dimensional case. It doesn't mean that the odd dimensional case is easier. Careful. That you have more representations doesn't mean actually, or more different types of representation doesn't mean it's easy. It's easier in the odd dimensional case. I would be actually with that one a little bit careful. Probably actually, at least in the lower dimensions, the even dimensional case are easier to calculate. For instance, if you go for the, let me spin 4 representations, and let's look at it from the spin 4 representations for 2 reasons. First of all, it's easier to understand. And second, it's also easier to calculate. Because for the spin 4 representations, you can use a kind of trick. The trick is basically that spin 4 is actually spin 3 times spin 3. So spin 5 is different. That's actually, there's no decomposition for spin 5. Spin 6 then is again easier because that's basically corresponds also to SU4. But spin 4 representations have the following. First of all, the group is relatively easy to write. You take all vectors in R4 in terms of Clifford algebra, and you multiply always an even pair on them. So you basically take an even pair. It's also basically, you could also simply say I take all bivectors and take products of bivectors. That gives me always spin 4. It's basically here in the even subalgebra, but that's not so important. Important is, that's what I said, we said with spin 3, that is actually spin 3 times spin 3. You can actually take an element and you can take these guys. It's relatively easy to see that E1, 2, 3, 4, if you take that part, that this part basically is just a projector. So, I mean, it projects basically in the Clifford algebra CL04, you have basically a null cone. You have 0 divisors. 0 divisors is basically, and they form a cone. And omega plus and omega minus, geometrically, you can simply see that one as a projection on the cone. So, and with that projection, you can split it into 2 parts, which I wrote here as S and Q, where both are actually from spin 3. So you have omega plus and omega minus, and basically the projection they can project down into each of them. And that's basically one thing which makes calculations in this case much easier. On the other hand, well, much easier in Qt. On the other hand, it still contains the whole thing. The only problem is we can use that one, and we are going to use that one, but in fact, in the general case, then would have to use all of them. So let me now go to the representation spaces. The point is basically the following. If you look at it, when you make that decomposition, you can actually write it down as a kind of stream. Each element which I put here is an irreducible piece. So each of these indices here is an irreducible subspace. It's indexed by the integers and the half integers. And well, this line and the blue line, each one actually corresponds to a pure spin 3 case. So that's spin 3, and that would be spin 3. And these are basically combinations. Vertically, you can basically see the representations. So 0, 0, these are the integer representations, and they correspond to our H representations. And these are all harmonic polynomials. If you go in terms of these simplicial functions, you are in this case, and they are all harmonic polynomials. If you write them out as polynomials, you will simply see all of these, case 1 and 2, they are harmonic polynomials. Simplicial, because you basically fetch them up, and harmonic. While the other ones, the intermediate ones with the half integers, are monogenic polynomials. They are basically also simplicial and monogenic polynomials, so in the kernel of the Dirac operator instead of, well, they also are harmonic, of course, but they are principally monogenic. They're also not scalar valued. So, and the problem is now we want to work with them. The point basically is the point basically is if you want to use now the case of the calculus of Ruzhansky-Turunen-Wirth, you don't actually work with the representations, even if formally you actually build everything, but rather with the coefficients. And the coefficients are matrix valued. So matrix valued or operator valued, depending on Boca and the things. So in our case, The lattice is rather easy. For the lattice, we basically have to take the integers and the half integers together. The representations we can basically write down shortly in this term. It's a short thing, but in fact, you have to basically use a projection like I wrote before, and then you can basically do that kind of thing. And the matrix dimension of each of them is basically nothing else than this here. So this is basically just the dimensions of each of the representations, and they are basically splitting up. And of course, and that's the important thing, they have a 3-term recurrence relation. So between them, which basically means that you can build one by the use of others. And additionally, you also know they must be orthogonal polynomials. That's actually important. At the moment where you have polynomials with a 3-term recurrence relation, you always know there are orthogonal polynomials behind. Point is, again, you don't work exactly on the polynomials, you work on the coefficients. The difference operators work on the coefficients, so you need actually to switch. And that's basically the hardest part in the calculations. If you really want to apply that method, is exactly in that step. You actually, instead of working with the representation, you write down the representations, but then you have to calculate what are the coefficients, and you have to switch the operators acting on the representations over to the difference operators acting on the coefficients. And that's basically the thing. That's actually the hardest step in the calculations. At the moment where you have that part, then everything else is a kind of nice way of working with. So in our case, we actually basically have to look what are the relations for the matrix coefficients. Well, the left and right translations are basically written down here. You basically just let them act. In this case, I let them just act. In principle, I should let them act on both sides, but I can simplify that case just by letting the thing act on one side only. So that's basically why I let them act only on left and the right. So, and the differential operators coming up from that are these guys, which are acting on them. So these are basically the things, the differential operators here, which are act. And it's easy to see these ones are left invariant and these ones are right invariant. That's basically easy to see when you actually write them down. And you can also see the symmetry of them. And of course, they are kind of split there. But then the splitting comes really from this splitting we are actually using. So, and when we have them, then of course, we can now basically look more closely. Instead of these ones, we can use the combinations of them, which is easier. That's these large D operators as left invariant operators. In particular, we take the first two, and then we take the commutator for them. And the Laplace-Beltrami operator for spin 4 basically would be then the summing up of all of them. And if you have them, basically it's easy to see that actually the spaces, our H representation spaces, are actually eigenspaces of the Laplace-Beltrami operator with eigenvalue, with these eigenvalue. Basically, you're summing up here. So that's basically how one can come up to them. And principally, we like, especially in the examples later on, we work with D. That are the differential operators which work on spin n functions. So the group Fourier transform is now straightforward after all of that. I mean, it's just writing it down. We have our representations written in this form. They are basically spin 4 representations written like spin 3 times spin 3 representations. And the Fourier transform is just formally basically integrating over spin 4 against the representations. And that gives you the coefficients, the lattice coefficients, L1, L2. The sequence spaces now, they're also basically straightforward. We basically take our lattice here, our points, and then associate with that the matrix, which is basically of the dimension complex valued of this, of the dimension of the DL1, DL2. And we basically have that the L2 norm of the whole thing is just a summation with the Hilbert-Schmidt norm of sigma. I mean, that's operator valued or matrix valued, and weighted with the size of the dimension. I mean, that's basically now we have everything before, and that's basically just writing it down. It's nothing else here than that part. The calculation is actually really in the matrix coefficients and in the differential operators and that part. So this part is only writing down. And then also, this one is now basically automatic from the construction. I mean, that's the advantage of this calculus. You know what to do. So if you just basically follow it, you have to do the calculations. There's no way around. But you don't have to guess. You just calculate, and you know whatever you calculated, that must be the correct piece you have. There's no need to actually now guessing or playing around with it. And that's the same thing here. With the group Fourier transform defined like that, with the lattice and so on, you basically have immediately that the Fourier transform is unitary of that type. I mean, that's basically the right norms and so on. And you have, of course, Plancherel identity or Parseval identity for these two things, for this thing, which is basically, again, only for this. And if you want to go to distributions, it's usually by duality. That's, of course, the same thing when you go that one. The only thing you have to be a little bit careful with the distribution is you have then discrete distributions, which is also rather kind of neat. So basically you take the dual with respect to the lattice. So, and there are kind of small tricks one can play around with that one. Basically, like here, power series and so on. That's a little bit, but that's another topic, but it's around funny, that part. So Sobolev spaces are also kind of automatic. We have our Laplace-Beltrami operator. The Laplace-Beltrami operator basically gives us the weight we have to put. And for that one, we can now basically say, okay, the Sobolev space is just defined of the power bus by basically that the Laplace-Beltrami operator of the same order is applied to F is just in L2. And you basically have the representations applied to F is in small L2. So basically that part. And small, well, the equivalent of the test functions, the rapidly decaying matrix sequences, which is also defined in that way. So you have basically gamma here. Rho basically maps lattice into the union of all these matrices. The dimensions basically are given, and also the norm basically is given, or the supremum for any number n. So, and of course with that part, we have the usual thing we would expect from a Fourier transform, that you have these isomorphisms from C infinity and T prime. So this again is just written down out what was actually constructed before. Now, the pseudo-differential operator calculus comes now basically also automatic of that part. We have our left invariant operators, which we can basically write down in this way. So the left invariant operators are written down in that way. And if you want to have examples of left and right invariant operators, basically from our previous ones, the initial ones we have, you have here, you have basically the symbols for that one, for the left and right invariant. Daggers are always with the right and the other ones in the left, and basically combinations of them. That's basically our first order. And they basically generate everything of the first order operators here. So that's basically just that one. I don't want to use actually D1 or D2 for it now. That comes afterwards. And the difference operators.
Uwe, can
Yes?
can you remind what are the sigmas? Sigma is
Which sigma?
no explicitly the sigma in the symbol. When you write sigma plus minus I1 plus
well, it's basically the sigmas are the spin tree symbol. Basically, let me actually go back here. Just a moment. No, not just a moment, just a moment. I can show. Wait, where I have my different here. You have these guys, and the Q ones only work, and you have the decomposition. The decomposition, which I actually put here, well, let me actually take, you have this decomposition in S and omega. You see this decomposition here, right? So S is in spin S and Q are in spin 3. So, and these Qs, the initial ones, they are basically this part, and I can write the symbol just down for them, just down in Q or just down in S. And the sigmas are basically just the symbols for the spin. The sigmas are just the symbols for these operators, Q plus minus 1 in spin 3. And then I just basically just take the tensor with the identity in the S. That's all.
And on spin 3, they should be the same as on SU2, I guess.
Yes, yes. They're basically the same as in your paper on SU2 there.
Okay, good, thank you, yes.
Actually, we actually even constructed them to make sure that they actually look exactly the same as yours. So, and the difference operators, basically they come here in this way, that they basically, you have basically these multipliers. So you take them from these multipliers, and then you basically, that gives you the parts. How to write them out, it depends a little bit. I mean, I can give you the explicit formulas, but I just wrote here an example for this Q, how you can basically is. So that's basically the difference operators written out for one specific one here, because the formulas itself are rather tedious and are rather large. I mean, I can give you them in from the paper, etc., but they're really, if you write them out, they're really rather large. The Hermander classes are, of course, in the usual thing, just like your one is used to. Basically, that's the machinery now again. We have calculated everything. We have the parts. So that's the point, basically, what we, and now it's basically just really milking it from the abstract theory, basically, just writing the abstract theory out. So, and also the hyperellipticity condition, if you look at it, it's basically the standard one adapted to this part. So here's basically just picking up the abstract theory. We have the machinery, we have the things, and then we can basically write it down. And this is basically what is actually this part. I mean, from the abstract theory, that's just the classic one you're all familiar with. Now, the question is simply how it works actually in the examples. Well, as a first example, we basically use the simplest one. I gave you the simplest one just from my operators D3Q plus a constant, and then the symbol you can immediately write out. The symbol is basically just this. And then it's rather easy to see. The only part where you have problems with invertibility is the first part where you have to look at. And that bond, you know, that is invertible if the constant is not I times the constant, not a half integer. These are all half integers. So basically, if that one doesn't happen, then this is never 0. It's basically just always a diagonal matrix. So that's not a problem. As long as is that one and you have the inverse as then an operator of 0 and it's globally hyperelliptic. The more interesting example comes now from if you look first at the so-called partial Laplacians. Because if you look at the partial Laplacians, LQ and LS, I can write it down their symbols. And then basically each one vanishes for their respective things. So if I actually have L1 to L2, the second one vanishes if L1 equals to L2, and the first one actually vanishes if it's exactly, instead of that line, it's the other line. And one of the things which comes out is basically if I take here Xi positive, then this one will be always an elliptic operator. Simplest example, take Xi equal to 1, and it's always elliptic. But the funny part is what happens in the negative case. And interestingly enough, that gives us a number theoretical problem. Why? Because if you look at now at this operator, then okay. Then this operator can be an ultra-hyperbolic operator or can be an elliptic operator, or hyperelliptic operator, based on what actually this here is. I mean, the first case you immediately have is if she is 1, then this one's an ultra-hyperbolic operator. So there's no chance to get ellipticity there. But if you look at the symbol, one realizes another thing. Well, this guy here actually makes sure that if we have an irrational phi, we have a chance that the symbol is invertible. In fact, then the symbol is invertible because there's no cancellation. If it's rational, of course, there will be a combination of L1 and L2 where you get a 0. But for an irrational one, that doesn't happen, as long as L1 and L2 is, of course, different of 0. Now, the question is simply, but that's not enough for hyperellipticity. We need a certain decay condition. And the decay condition is basically down here. That's our decay condition. And if you look at it, that's the same condition you have when you actually ask yourself, how far is an irrational number from a rational one? And that's called, and the function which satisfies this one is actually called a Liouville number. An irrational number which actually has that kind of decay. Basically, think of that part. You take a number, irrational number, you take the continuous fraction approximation, infinite, and then you cut off. And then you ask yourself, okay, if I cut off, what will be the approximation order? That's basically what the question here is. And Liouville numbers are the ones for which you have such a decay condition, which corresponds actually to the condition we have for our case, for the hyperbolic. And so if it's a non-Liouville number, then basically that condition doesn't hold. And that's basically what we want there. Just for practical purposes, if you think about it, I don't know, might be a little bit longer time. Think on that part, Liouville numbers, typical Liouville numbers are irrational arctangents and so on. Non-Liouville numbers are actually algebraic numbers. For instance, square root of 2, square root of 3. They are basically algebraic roots, and they are basically, that's a kind of funny, they are actually the farthest away from rational numbers as you can be. So if you want to have irrational numbers which are far away from the rationals, the farthest away are actually really the algebraic roots, like square root of 2, square root of 3. If you take basically things like certain logarithms or arctangents and things like that, then you are actually in the case of the Liouville numbers. You can even actually use mu as an order to describe how far they are. And that's basically here what we actually can use. That gives us here actually something that we can simply say that operator's hyperelliptic for irrational non-Liouville numbers. So you need an irrational number, non-Liouville, and then it's hyperelliptic. And then, of course, you get the estimates like I have here. And I also get the subelliptic as estimate, and as one would expect, the loss of 2 mu derivatives. So, and here you can see basically how in these calculus basically problems pop up, which originally one wouldn't have thought of. At least I wouldn't have simply guessed that the condition of hyperellipticity suddenly becomes a condition of difference between rational and irrational numbers. So. But let me stop here. It's almost 10 o'clock, so I also don't want to overdo it. And thank you very much for your attention.
Okay, thank you very much for this interesting talk. Of course, now many connections with number theory, which was not expected. So we are open for questions. If someone has a question, please.
So maybe I ask just one remark. I have one remark because because I have to go to defense. But yes, I think this is very interesting, and actually I can send you. We have some open conjectures in particular for related to sublaplacians, and I think that different characterizations, for example, of Gevrey spaces related to sublaplacian, and I think that we proved with you too For the Heisenberg group in general, we don't know, but I think that you can also do, now that the formulas that I have seen, I think you can also answer these questions for this in 4. So I will not give maybe more details, but I'll send you a paper which I have in mind. So yeah,
That would be excellent. Thank you.
work.
Okay, thank you. So, more questions or comments?
May I ask you?
Yes.
Okay.
Yes.
Okay, thanks for a nice talk. You just mentioned Gelfand pair. I'm just wondering, is there calculus for Gelfand pair as well? You have, or it's just for
Yes.
particular case of this? You already have calculus for Gelfand pair, like Ruzhansky-Turunen-Wirth calculus?
Well, actually, simplified, let's say. Yes, you have it. You can do it. I think there are some papers on that, but the point is, it's kind of simplified ones, because basically what you do is, what happens in the Gelfand pair is basically that you take these matrix valued operators and you basically average them. It's because you just have one. I mean, in the Ruzhansky-Turunen calculus, you basically have you have matrix valued, and the matrices become bigger and bigger when you go up. But in the Gelfand pair, you basically, since you factorize out these lower dimensional compact subgroups, you always have one for each dimension. So, which simplifies the thing, but it also means basically that you're kind of averaging the whole thing. I mean, that's like if you take a group which has a high-dimensional group, and then you basically take the character, because a character for a non-compact group, for instance, persons don't work with it because so much with it, but you can do it. It's just averaging your representations in one.
No, I mean, you have this. You're talking about compact kind. It's for non-compact. Like you consider like a unimodular group, and then consider Gelfand pair, and there is a calculus.
Yeah, you can do that.
No, but like already existed, or one can do it. That's my point.
If there exists a general pseudo-differential calculus, I'm not sure. I mean, persons use it principally for constructing approximation functions and other things, etc. So if you want to construct wavelets and other parts, it's basically used there, and Fourier transforms. If they ever use the Fourier transform, I mean, Fourier transforms on that one exist. If there's ever a general pseudo-differential operator calculus in such case, if somebody wrote that one down, I don't know.
Okay.
At least I haven't seen it. I have seen specific cases.
Okay, a specific case of like which case you have seen?
Now, for instance, well, the simplest case where everybody likes to use is a sphere. If you take the sphere, basically that's type of, I mean, sphere and Rn, you take SON, you factorize SON minus 1 on one side. Then basically you still have lots of spherical harmonics.
Yeah.
So you factorize on the other side, and then basically everything just becomes dependent on the angle between the point and the direction. So, and then if you write the Fourier transform down in terms of these ones, you only have one basic for each power. And if you write them down, then it's exactly the Gegenbauer polynomials. So you take basic for each power, you take the corresponding Gegenbauer polynomial.
Okay, and these spin groups are also related with somehow with Gelfand pair, or is just independent, like, because you mentioned.
Well, you can also use it for the Gelfand pair. I mean, if I want, for instance, to write down one of the things you want, for instance, for the sphere, if you use spin n, is there's a so-called Funk-Hecke formula, which is basically that you just want from the things, and that's still the typical result of a Gelfand pair, because you basically take spin n. You factorize also spin n minus 1 on one side, but then you basically take all lower dimensional rotations, so spin n minus 1 on the other side, and then you also end up with a Gelfand pair. Gelfand pair, typically when you just really want to have one polynomial for each power.
Okay.
So if you really want to do complex analysis and so on, usually persons like to do these kind of things, because then suddenly you can work. I mean, one of the reasons why complex analysis works so wonderfully is each power of Z, there's only one. There's no more.
Yeah. Thank you.
Okay, thank you. Any other question?
Yes, I have a question. Thank you, Professor, for your talk. In one slide, you had that you have the decay of the diagonal of the symbols.
Yes.
This is because you are working explicitly somehow with the weights, or is because behind you have like SU2 times SU2?
That one, that's basically, that actually comes from the construction. So spin. I mean, the same thing you also have in spin 5 or 6 or so, if you want. That's not actually really that you, for that one you don't really need the decomposition for SU2. The problem is what you would need here for that part is that you actually, well, SU2 times SU2, if you want that one, or that's actually really coming only because you want to have an easy way of calculating. At a certain moment, you simply like to do that here. If you would go for spin 4 and spin 5, or spin 5, spin 6, you can do that. Then the problem is basically that the symbols are not that nice looking. Then suddenly really actually the things become kind of, well, I wouldn't really say a horror to calculate, but not very beautiful or not very nice looking. I mean, one of the things we don't really know yet is a very nice way of looking at and then getting nice, really nice formulas. Not just basically, I mean, you can always calculate and you can present the results. The other thing is writing it down in a way that it's actually compatible with what exists and so on. You don't just want to have results, you want to have results which are also basically fit in the existing scheme, what persons have.
Okay, thank you.
But here, it's really just the group. So on spin 4, spin 5, spin 6, spin n, we would have the same thing there. That's actually basically just really coming from the abstract.
Okay. Thank you, Santiago, which is our co-organizer. Any other question?
Maybe you could very quickly comment on where we get problems and what kind of problems we get if we go to non-simply connected groups like SO and instead of the spin groups. Thank you.
Well, the problem basically is if you have, well, it's actually, I would say it's actually more from the applications, because for instance, I don't want to integrate, if you go for diffraction tomography or so, I don't want to integrate over non-simply connected groups. I mean, the problem is basically, you have to be careful there with, well, it's really from the applications. I would say you could do the whole thing calculus here. Probably you can also do for SON, but the problem is from the applications, that's the thing you don't want to do. I don't want to, in diffraction tomography, I don't want to go for integrating really over non-simply connected domains. I also don't want to actually, same thing also when I'm going for the things, if you take well, if you take the fermion, or even if you go over then fermion boson game, right, where is it here? I don't want to actually look at the states and so on in simply connected domain, because I want to have my polynomials, my functions, everything over nice domains, not actually suddenly have to think about what happens if they are separated, if they're multiply connected and so on, and work with different boundaries and all that stuff. That's rather a troublemaker. So if I can avoid it, I like to. Sorry. But that's really actually the main reason why I actually don't want to do that. It's really from the application point of view. Last thing I want is actually having trouble there.
Okay. Well, I have a question, but myself, if for the digital differential operators, did you identify the order of singularity of the kernel? if you recover, let's say, Calderon-Zygmunt operators and these things. That should be nice if you want.
Well,
Nice if you want
we
applications.
didn't do that.
Oh, okay.
Yes, but you can do basically, I mean, that's the nice thing. That's the nice thing with the whole machinery. At the moment where you have established the things, I mean, one can do that. You can look for Calderon-Zygmunt operators, you can look for Michelin multiplier theorems, you can look for Borchberg lemma, etc. That's actually the nice thing in this machinery. You get all the right tools, and then it's basically really working from there. That makes it actually so nice.
Well, so conjecture is that you can recover all the Calderon-Zygmunt theory that one has for the case of compile groups, yes?
Yes.
Okay, thank you. Okay, so more questions? Okay, if not, then thank you very much, Professor Kähler, for your very interesting talk. So the next section, we will have Professor Girl Group. So we will send the announcement at the end of this week. So thank you. So see you all in the next opportunity.
Don't forget to remind them of your conference.
Yes, I will send a final reminder today. So here, Professor Cerejeiras, yes, will give a talk on in the conference. Okay, so see you all. Bye-bye.
Thank you very much,
Thank
Uwe,
you.
for this
See you.
interesting talk.
Thank you very much
Bye.
for the talk. See you.
See you.
Goodbye.